Welcome back to The Explainer. Today, we're diving straight into the invisible laws that govern electric charges and fields. We're going to unpack the fundamental principles of electrostatics, which, is the study of forces, fields, and potentials that arise from static charges. And to really ground this, we're going to start with a phenomenon that you have almost certainly felt firsthand.
You know the exact feeling, right? You slide out of your car seat, you reach out to shut the door, and zap. Or maybe you're just taking off a synthetic sweater in a dry room and you hear that distinct crackle. So what's actually happening there? Well, what you're experiencing is the rapid discharge of accumulated static charges. When you rub against certain insulating surfaces, like your car seat or that synthetic fabric, charges build up on your body. And the second you touch a metal door, all those accumulated charges just rush to discharge. It is literally the exact same fundamental process that causes massive lightning strikes during a thunderstorm, just on a much, much smaller scale.
Here's our roadmap for today's explainer. First, we'll cover the nature of charge. Then, Coulomb's law of force. After that, mapping the electric field, understanding electric dipoles, and finally, electric flux and Gauss.
Let's jump right into Section 1, the nature of charge.
Our modern understanding of all this actually traces its roots back thousands of years. Around 600 BC in Greece, Thales of Miletus noticed that if you rubbed a piece of amber with wool or silk, it would suddenly attract really light objects like straw. In fact, the very word electricity comes from the Greek word elektron, which literally just means amber. Fast forward a few centuries, and scientists began to realize there were exactly two distinct kinds of electrification. Bring two rubbed glass rods together and they repel, but a rubbed glass rod and a rubbed plastic rod, they attract. It was actually the American scientist Benjamin Franklin who figured out that these two types of charges can completely neutralize or nullify each other's effects. Because of that mathematical cancellation, he elegantly named them positive and negative.
And this underlying nature is exactly why different materials behave so differently when they're charged. Take conductors, like metals, the earth, and, the human body. They contain electric charges, specifically electrons, that are comparatively free to just roam around inside the material. That's why a static shock travels so easily right through your body to the ground. But on the flip side, we have insulators, like glass, nylon, wood, and plastic. These put up high resistance to the passage of electricity. If you place a charge on an insulator, it basically stays exactly where you put it. So you can build up a nice static charge on a plastic comb, but a metal spoon, it just leaks the charge right through your conducting hand.
Now there's one more absolutely crucial property of charge we have to talk about. Charge isn't some continuous, smooth fluid that you can just infinitely divide. It doesn't work like that. Instead, charge is quantized. The experimental reality is that all free charges in the universe are integral multiples of a basic unit of charge, which we denote with the letter E, and that's the charge carried by a single electron or proton. So the total charge Q on a body is always an integer n multiplied by E. You simply can't have half an electron's worth of charge. Now, we don't usually notice this grainy nature of charge on a macroscopic scale because E is incredibly tiny, but it is a foundational rule of the universe, and it was beautifully demonstrated by Millikan back in 1912.
Moving right along to Section 2, Coulomb's law of force.
Enter the French physicist Charles-Augustin de Coulomb. Back in 1785, he acted a bit like a scientific detective. He set out to measure the invisible electrostatic forces pushing and pulling between charged metallic spheres. To do this, he invented an incredibly sensitive piece of equipment called a torsion balance, which let him measure these really minute forces of attraction and repulsion. By cleverly dividing charges exactly in half, basically touching charged spheres to uncharged identical ones, and then meticulously changing the distances between them, he completely cracked the mathematical law governing their interaction.
And here's what he found. Coulomb's law states that the force F between two-point charges is directly proportional to the product of their charges, so Q1 times Q2. But most importantly, it varies inversely as the square of the distance between them. That's the r squared you see at the bottom of the fraction. Think about what that actually means in practice. If you double the distance between two charges, the force doesn't just cut in half, it plummets to 1/4 of its original strength. The force drops off dramatically the further apart those charges get.
Which brings us to Section 3, mapping the electric field. So how do we visualize this invisible force? Physicists use electric field lines. Honestly, think of them like a topographical map, but for electrostatic forces. Let's walk through the definitive rules for drawing them. First off, they always start at positive charges and end at negative ones. Second, if you draw a tangent line to any point on a curved field line, that line tells you the exact direction of the net electric field right at that spot. Third, two field lines can never cross. If they did cross, it would mean the field has two completely different directions at a single point, which is obviously impossible. Fourth, the relative density, or how close the lines are to each other, indicates the strength of the field. Crowded lines mean a strong field, spread apart means it's weak. And finally, they form continuous space curves without any breaks.
Next up, Section 4, Understanding Electric Dipoles.
An electric dipole is exactly what the name implies: two poles. It's a pair of point charges, one positive Q and one equal but opposite negative Q, separated by a specific, usually very small, distance that we call 2a. The line connecting these two charges essentially gives the dipole a direction in space, and by convention, it points from the negative charge to the positive charge. We quantify all of this using a vector called the dipole moment, represented by the lowercase letter p, and calculating it is easy. It's simply the charge Q multiplied by that separation distance, 2a.
Now, when we start comparing these fields at a distance, a really fascinating difference emerges. If you look at a single isolated point charge, its electric field drops off as 1 over r squared, just like we saw with Coulomb's law. But remember, a dipole is a positive and a negative charge sitting right next to each other. Their total net charge is technically 0. So if you're looking at them from far away, their electric fields very nearly cancel each other out. Because of this near cancellation effect, the electric field of a dipole falls off way faster at large distances, specifically as 1 over r cubed. And this isn't just some abstract math concept. A ton of molecules in the real world naturally have their positive and negative centers slightly separated. We call these polar molecules, and water, good old H2O, is the classic perfect example of a permanent electric dipole.
And finally, we arrive at Section 5, Electric Flux and Gauss. Okay, to really grasp Gauss's law, we first have to build up the concept of electric flux. Let's break it down into 3 easy steps. Step 1. Picture those continuous electric field lines we just mapped out flowing through 3-dimensional space. Step 2. Imagine placing a surface area, like a flat square or maybe even a curved balloon, directly into that flowing field. Step 3. Simply count the number of field lines that are physically cutting through that surface area. That count, that is your measure of electric flux. It's super analogous to holding a bucket out in the rain to catch water, where the flux would be the amount of water actually passing through the opening. The key difference here is that there's no physically observable substance moving, we are just mathematically capturing the field's intensity over a specific area.
And that idea forms the entire foundation for Gauss's law. What Gauss's law does is elegantly summarize a deeply profound truth. The total electric flux through any closed surface is simply equal to the total charge Q enclosed by that surface, divided by a fundamental constant called the permittivity of free space, or epsilon naught. Think about how crazy that is. It doesn't matter how large the surface is, it doesn't matter where the charge is located inside it, or how the flux is distributed across the surface itself. The grand total flux is fundamentally and inextricably linked to only one thing: the exact amount of charge trapped inside.
Because of this, Gauss's law gives us immense practical power in physics. First of all, it holds true for any closed surface, no matter how weird or complex its shape might be. Second, if a surface encloses absolutely no net charge, the total net flux through it is guaranteed to be exactly 0. Every single field line that enters that surface has to exit it somewhere else. Third, by choosing a clever symmetrical Gaussian surface, say a cylinder around a long wire or a sphere around a point charge, it dramatically simplifies calculations that would otherwise be total mathematical nightmares if you only used Coulomb's law. And finally, it easily proves fascinating, non-intuitive realities, like the fact that the electric field everywhere inside a uniformly charged, hollow, thin shell is exactly 0.
As we wrap up this explainer, I want to leave you with one final, kind of mind-bending thought. Look around the room you're sitting in right now, from the screen you're looking at, to the chair you're sitting on, to the adhesive holding your shoes together. Normally, these everyday materials are electrically neutral, but at a microscopic level, they are absolutely packed with the charges we unpacked today. The forces holding atoms together to form solid objects, the surface tension of the water you drink, the very structural integrity of the physical world you interact with every single day, all of it is basically electrical in nature. It all arises from the precise push and pull of these invisible electrostatic fields. So, what does this all mean? It means the equations you just explored aren't just abstract physics, they are quite literally the glue of the universe. Thanks for joining me on this explainer, and keep exploring.